Imagine an electric car that can drive over 600 miles on a single charge. And when it finally runs out of power, you plug it in, walk away for a quick 10-minute coffee break, and return to a battery that is fully charged. No range anxiety, no long waiting lines at charging stations, and zero risk of the car catching fire. This is the promise of solid-state batteries. It has been called the holy grail of energy storage, a technological leap that could finally spell the end for gasoline cars. But what exactly is a solid-state battery, why is it taking so long to build, and how close are we to actually seeing them on the road? Today, we are going to break down the science, the challenges, and the multi-billion-dollar race to build the ultimate battery. To understand why solid-state batteries are such a massive breakthrough, we first have to look inside the batteries we use today. Whether it is in your smartphone, your laptop, or a modern Tesla, almost every electric device runs on lithium-ion batteries. These conventional batteries have three main parts. First, a positive electrode called the cathode, usually made of lithium metal oxides. Second, a negative electrode called the anode, typically made of graphite. And third, a liquid chemical puddle called the electrolyte. When you charge your phone, lithium ions are forced out of the cathode, swim through the liquid electrolyte, and tuck themselves into the graphite anode. When you use your phone, the process reverses. The liquid electrolyte does a great job of letting ions swim back and forth, but it has a major catch-22, it is highly volatile and flammable. If a battery is punctured in an accident, or if it overheats due to a manufacturing defect, the liquid electrolyte can catch fire. This triggers a chain reaction called thermal runaway, leading to intense, self-sustaining chemical fires that can burn for hours. To prevent this, electric vehicle makers have to pack their cars with heavy cooling systems, protective steel armor, and complex monitoring software. This adds hundreds of pounds of deadweight, reducing the vehicle's driving range and increasing its manufacturing cost. Solid-state batteries solve this liquid dilemma by removing the liquid entirely. Instead of a volatile chemical fluid and a thin plastic separator, a solid-state battery uses a solid sheet of material to act as the electrolyte. This solid barrier can be made of specialized ceramics, glass, or solid polymers. Because the electrolyte is solid, there is nothing to leak, vaporize, or catch fire. Solid-state batteries are incredibly stable, even at temperatures that would cause conventional batteries to melt down. By removing the fire hazard, we can throw away the heavy cooling systems and protective shielding, making the entire battery pack lighter, simpler, and much cheaper to build. But safety is just the beginning. The real superpower of solid-state batteries lies in how they unlock the anode. In a standard battery, we use graphite for the anode because it acts like a sponge, holding lithium ions safely inside its molecular pockets. But graphite is heavy and bulky. Since a solid ceramic electrolyte is physically tough, we can completely eliminate the graphite. Instead, we can plate lithium ions directly onto a paper-thin sheet of pure lithium metal. Pure lithium metal is the ultimate anode material because it is incredibly light and can pack ions much tighter than graphite. This doubles the energy density of the battery, allowing us to squeeze twice as much energy into the same amount of space. So, if solid-state batteries are safer, lighter, and hold double the energy, why isn't every car using them? The answer lies in a microscopic nightmare called dendrites. During fast charging, lithium ions rush backward to the anode. Instead of coating the lithium metal sheet in a flat, even layer, the lithium atoms tend to cluster together, forming tiny, needle-like metallic structures. These needles are called dendrites, and they behave like slow-motion lightning bolts. Over multiple charge cycles, these dendrites grow longer, finding tiny microscopic cracks in the solid ceramic electrolyte. Eventually, they punch all the way through to the cathode, causing a short circuit that kills the battery instantly. Another major engineering challenge is solid-to-solid contact. In a standard battery, the liquid electrolyte is wet, so it flows into every microscopic crevice, maintaining perfect electrical contact. But in a solid-state battery, everything is rigid. When the battery charges and discharges, the pure lithium metal anode physically expands and contracts by up to 100%. As the anode shrinks during discharge, it pulls away from the solid electrolyte, leaving tiny empty pockets. This separation blocks the flow of lithium ions, causing the battery's performance to drop rapidly. To stop this delamination, many current designs require massive physical clamps or springs to keep the battery under high pressure, which adds weight back into the system. To overcome these hurdles, scientists are experimenting with three main chemical pathways. First are polymers, which are flexible plastic-like materials. They are easy to manufacture using existing factory lines, but they don't conduct ions well at room temperature. Second are oxide-based ceramics, which are incredibly hard and safe, but brittle and difficult to manufacture in large, thin sheets. Finally, there are sulfide-based glasses. Sulfide glasses are soft and conduct ions incredibly fast, but they have a dark side. If they are exposed to moisture in the air, they react to produce highly toxic hydrogen sulfide gas. Every battery manufacturer is betting on a different mix of these materials to solve the puzzle. Even if we solve the chemistry, we still have to face the economics. Today, conventional lithium-ion batteries are cheaper than ever, costing around $100 to $130 per kilowatt hour. This low cost is the result of decades of manufacturing scale. Solid-state batteries, however, are currently handmade in high-tech laboratories. Because the materials are sensitive and the assembly requires specialized cleanrooms, early prototype cells cost upwards of $500 per kilowatt hour. For solid-state to succeed, manufacturers must design completely new automated assembly lines that can produce these ultra-thin, delicate ceramic layers at scale, bringing the price down to that magic $100 threshold. Despite these challenges, the automotive industry is investing billions of US dollars to bring solid-state batteries to the market. Toyota, which holds the most patents in the field, has partnered with energy giant Idemitsu to mass-produce sulfide-based solid-state batteries, targeting commercial release in cars by 2027 or 2028. QuantumScape, backed by Volkswagen, has developed an anode-free ceramic separator and is already shipping prototype cells to car makers, proving their batteries can retain 95% of their capacity after 1,000 charge cycles. Meanwhile, Samsung SDI has built a dedicated pilot line and plans mass production by 2027. We are standing on the cusp of a major transition. While solid-state batteries will likely start as premium options in luxury vehicles and sports cars, their eventual mass production will change everything. They will not only double the range of electric vehicles but could also enable electric airplanes, massive grid storage, and consumer electronics that last for days on a single charge. The search for the holy grail of energy storage is no longer a laboratory dream, it is an active industrial race that will define the future of transport and clean energy. Would you buy an electric vehicle today, or are you waiting for solid-state batteries to hit the market? Let us know in the comments below. If you want to stay curious and learn how the tech of tomorrow works, make sure to hit that subscribe button for Layman's Field, bringing knowledge for everyone. Thank you for watching, and we will see you in the next field.